Here we go. All right. So we're talking about normal distributions. We're talking about variables that are normally distributed, in other words, bell curves. And this is example 3, part A. Now, we're about to transition into a different sort of question that's related to what we've talked about. But anyway, according to TrueCar.com, the nationwide purchase price for a Mercedes-Benz convertible is normally distributed. Those are important words there because that allows us then to draw our bell curve. All right, those are important words there. And by the way, the premise of this is the fact that my son is quite the car enthusiast. I'll share this with you at the end. We'll work the problem and then you can watch it if you care to. But anyway, but notice here it says that the mean is $101,879. 101,879. That goes in the middle. This is not a standard normal. I want to remind you that a standard normal is one where the mean is 0, Z. All right, this is different. In fact, go back to the notes here. This is what I would call a general normal. The variable, therefore, is going to be X, just our go-to for any kind of variable. And it's more general. And we're going to talk about the idea of standardizing a score here in a minute. That'll be the key idea. And we'll talk about how to do that. But back to the question. So it says that the mean is 101,879. So I want to remind you that we use the symbol mu for the mean of a population, right? This would be the mean for that population of cars. And it says that the standard deviation is $1,430. All right? And that, if you recall, is called sigma. All right? I've been working on drawing my sigmas here. So there you go. Now, part A. What percentage of cars are purchased below dealer cost, which according to TrueCar.com is $95,849? Well, in reference to the mean, that dealer cost of $95,849, that's over here, right? And it says below dealer cost. So wouldn't that be all these cars that are purchased down here below that cost? That cost is below the mean, and below the dealer cost is below that. So there we go. Now, let's get used to writing this up as a probability statement. It says, what percentage, probability, what percentage of cars, all right, and our variable is X, so of all the cars, of all the Mercedes-Benz convertibles, which ones have a price? That's the variable X, the price. Have a price below this. Wouldn't that be written as less than that particular price, right? So what percentage of these cars are purchased at a price below dealer cost? So here's the probability statement, and then here's the picture. All right, so here's the problem now that we face, is that this table here only works for the standard normal, where the bell curve has a 0 in the middle. How many variables have a mean of 0? Oh, some do, but not very many. How would they possibly make a table for every combination of mean and standard deviation out there? It's impossible. So I always tell people that the standard normal is almost like the universal language, Z, right? That's the one that the table can speak. So we go, hey table, I got a picture for you. But the table says, I don't speak X, I only speak Z. All right, so in my silly analogy here, we have to translate this scenario to the language that the Z-score can understand. So the idea would be, I'm going to redraw this as a bell curve with 0 in the middle, standard normal. You would describe this as a lower tail, wouldn't you? All right, so let's draw the same picture here, but we're about to change the scale from the prices of these cars into standard normal. So the question becomes, how many standard deviations is that price from the mean? That's what a Z-score is. You guys remember when we talked about Z-scores weeks ago, we talked about the fact that a Z-score is how many standard deviations a particular value falls from the mean. All right? So we're about to do what they call standardize the score. And I hope you remember, this is back when we did measures of position prior to spring break. When we talked about Z-scores, we talked about how to convert a generic X into a Z, all right? So, we're now going to translate this into the probability that z is less than a certain number, and we need to figure out how many z's, we got to figure out how many standard deviations that price falls from the mean. And if you recall, our little interpreter for doing that was this beautiful thing. Z equals x minus mu over sigma. Remember that one? It's been a while. I want to say it was assignment number 7, if I'm not mistaken. Go back and look at measures of position when we talked about z-scores prior to spring break. But here's how we convert that price into a z-score. So here's the work in between here. I didn't leave a lot of room. I didn't plan ahead very well, sorry. But x would be that particular price, 95,849, minus the mean, 101,879, all over the standard deviation of 1,430, and that would be the z-score for that. I will now grab my beautiful calculator and do that. All right, so 95,849 minus 101,879. I'm making sure I type this in right here. There's a lot of pressure. If I mess up, it's on the internet forever, right? And then divide that, hit equals, right? Equal that out. And then divide that by 1430, and you get this crazy decimal here, okay? Now, one of the things we have to remember is that we're kind of dictated by the table as to where we round that z-score. This table, I want to remind you, takes z-scores out to 2 decimal places. So following that protocol, this would be negative 4.22. And that would be the z-score right here. And you know what? Now the table can help us out. All right? And here's the interpretation of that. That price, dealer cost, I believe they called it, is 4.22 standard deviations below the mean. All right? That's how many standard deviations that price falls from the mean. That's what z-scores are, just like they were back before spring break when we covered that. So now we can go to the table. I'm already there, never mind. Okay, now, maybe this was a poor example to start with, but this is like example number 1 that we enjoyed earlier. So we go look for 4.22, and this is that example you might remember where it's off the table, and therefore it's the footnote, right? Remember example 1, and it says use 4999 for any z values that are basically off the table. And 4999, remember, would be that middle sliver right there. Right? This table always, when you go to a particular z-score, it's that middle sliver. But again, the shaded area we want was this lower tail. So again, we use logic like we did on example 1. Go back and look at those again if you need to. But if we want to know what that lower tail is, the percentage of cars that are purchased below dealer cost, same picture, different scale at the bottom. Wouldn't we want to take the lower half of the bell curve? Sorry, this is really messy. I should have spaced things out better. Usually I'm pretty good about spacing out. But anyway, wouldn't we want to take that 0.5 and subtract that middle sliver of 0.4999, and we would get 0.0001. All right? That's that area there. That's that area there. I won't split hairs on this, even though I'm probably supposed to. I'm trying to show you a lot of grace, if you'll do the same for me. It did technically say what percentage of cars are purchased below that price. So let's change this to a percentage. I'll accept the decimal, but if you recall, you change decimal to percentages by moving it 2 places. So if you move that 2 places over and put a percent symbol on it, it would be 0.01%. And to me, that would be the best way to give the answer. So a very, very small percentage of these cars are purchased below dealer cost. That's what we're taking from that. All right, you can quit watching if you want. I'm done doing the math. I'll just show you the background on this. So my son has been a car enthusiast for as long as I can remember. He could identify cars when he was probably about 3 years old, maybe. And so anyway, many years ago, back when he used to talk to me, I'm just kidding around, son, all right? But anyway, he was messing around on TrueCar.com, and I just I just took a screencast of it. This is 2012. He was pretty young back then. But anyway, he was looking at Mercedes-Benz convertibles and looking at the data from TrueCar.com. And you're about to see, this is going to pop up on here, and they graphed the prices of these cars. And then my son looked at that and goes, "Dad, that looks like one of those things you play around with." And of course it is. And I said, "Yeah, that's called a bell curve, son." And the definitions of these prices that I'm using in this example are from TrueCar.com. So, in case you're wondering, and this is old data, it's 2012. You know, I can't update this every year, I'm too lazy. Okay, so you understand Mr. Siegel uses old examples, too lazy to change them. But dealer cost was defined by TrueCar.com. And these are the numbers I'm using throughout the rest of this example. So I just thought I'd share that with you. This is real stuff, and people do these things all the time. So anyway, there you are with that. Love you, son. Thanks for setting up a math question for me.